Let's pick up where we left. We have an algebraic extension k over f, meaning every element of k satisfies some polynomial equation over f. I want to understand the simplest kind of such extensions. You take just one element of k, little a, and you add it to small f. And you take the smallest field that these guys generate. That's f round bracket a. I want to know what f round bracket a looks like. I'm also going to let f square bracket a be the subring of k generated by the smallest ring, subring of k that contains both f and a. So potentially f square bracket a is smaller than f round bracket a. So we want to know what this looks like. The first observation is that there exists a surjective ring homomorphism. I've called it phi A, but earlier we had called it some sort of evaluation homomorphism from the one variable polynomial ring to this subring f square bracket a, defined by phi of f of a polynomial is the polynomial evaluated at a. By definition, fa lives in f square bracket a, because it's a polynomial expression in a with coefficients in capital F. What's the kernel of this? And by definition it's surjective, because you can check rather easily that f square bracket a really consists of all such expressions. Consists of all polynomial expressions in A with coefficients from capital F. And so this is onto by definition. What's the kernel? Well, the kernel by definition is all the polynomials such that f of A is 0. So this is the set of polynomials that A satisfies, that A is a root of. And because A is an algebraic element, that just means that there is some non-zero polynomial that A satisfies, so this kernel is non-zero. So this now is a non-zero ideal in your polynomial ring, which is a PID. It follows that this is a principal ideal some polynomial. How unique is this P? What freedom do you have for this P? Well, if you have a principal ideal in an arbitrary ring, this is, for a moment, forget polynomial rings. In any arbitrary commutative domain with 1, you have a principal ideal, let's say. If you have another generator, what does that mean? That means A divides B and B divides A. So A and B are related by some unit. The units in this ring are just elements, non-zero elements of F. So this P is uniquely determined up to a constant, up to some element of capital F. And I can sort of kill this freedom by choosing the top coefficient of P to be 1. So I can make it unique for a unique monic polynomial. Top coefficient 1 means polynomials that start like this. Okay? For a unique monic polynomial, take this as an exercise, if you wish, if it's not clear. Think about it a little bit, you'll see it. That the only freedom of choice we have for this little p is an element of capital F. So I can, if you have one generator, then any generator will be just a scalar multiple of it. So you can, if you insist that the top coefficient is 1, then there is no freedom at all. And this polynomial is called the minimal polynomial of A. Definition. Px is called the minimal polynomial of A over F. Another exercise, verify that P is really the smallest degree monic polynomial that A is a root of. So in fact, it's the unique monic polynomial of minimal possible degree that A is a root of. That Px is the unique monic polynomial of least possible degree that such that P of A is 0. Sometimes, I think in my notes I called it P sub A because it depends on A. So to give an example, if you take this polynomial, it's an example before going on. Just a little pause example. If you take A equal to e to the 2 pi I over 3, this is an algebraic number, and this is an algebraic over Q. What is its minimal polynomial? Well, it satisfies lots of polynomials, like it satisfies this one. It's a cube root of unity. Satisfies. But if you want a least possible degree guy, if you look at all the polynomial that it satisfies, that's an ideal, and that has a generator. And the generator is going to be least possible degree polynomial that it satisfies, and that is this one. So you can check that x squared plus x plus 1 is P is 0. So it does satisfy a degree 2 polynomial. It certainly doesn't satisfy a degree 1 polynomial because this is not a rational number. So it has to be at least degree 2. And if you look at degree 2 polynomials that it satisfies, then there are other ones, but they are just like this. Of course, scalar multiples of it are also going to be polynomials that A satisfies. So if you insist that the top coefficient is 1, then you have no freedom in the choice of this polynomial at all, and that's the minimal polynomial. And then we are saying that that's a generator for the ideal of all polynomials that A satisfies. For example, this one is in that ideal, meaning what? Meaning this one is a multiple of this polynomial. Indeed, x cubed minus 1 is x minus 1 times x squared plus x plus 1. So it is in that ideal. Okay. So that's the sort of thing we are talking about. Very good. So now what you have is, you have a surjective homomorphism to F square bracket A called phi A, and the kernel is generated by this polynomial P sub A. So, and P sub A is non-zero, you see, because this ideal is non-zero. So, by first isomorphism theorem, fx mod this ideal is isomorphic to f square bracket a. Now some magic happens. You note f square bracket a is a domain. Why? Because it's after all sitting in a field, and the field is a domain. Since it's sitting, it's a subset of a field after all. So there is no zero divisor. Okay. So it's a domain, so this is a domain. So this is a prime ideal. And it's non-zero, so it's a non-zero prime ideal. That's how you tell something is a prime ideal. When you quotient by it, you should get a domain in fx. But fx is a PID. Since fx is a PID, this is actually a maximal ideal. Okay, that's something very special about one variable polynomial ring. Non-zero primes are actually maximal. But if it's a maximal ideal, then this quotient is actually a field. So this thing, which was only a ring to begin with, actually happens to be a field. So that means f square bracket a is already a field. And it's a field that contains f and a. So f square bracket a is actually same as f round bracket a in this case, which was not the case if a was transcendental. For example, if you take a transcendental number like pi, these two things are not going to be the same at all. But in this case, they are actually equal. So what you get is that fa mod this minimal polynomial is isomorphic to f square bracket a, which is same as the field generated by f round bracket a. And this is the result that I was driving towards. I wanted to say I want to understand what this field looks like. Really, every element in this field to begin with is a rational expression, but now we see it's actually a polynomial expression, and they can be identified as such. And in fact, so if degree of this minimal polynomial is d, then we know that this field is an extension field of f of degree d. Then this k then this extension has degree d. And with basis, if you unpack this, see that it has a basis 1a square a to the d minus 1. This I'll leave as an exercise. This will be a good exercise to do. So the upshot is that if you take a element that is algebraic, it satisfies lots of polynomials, take one of least possible degree, and if you make it monic, then it's unique. You call that the minimal polynomial. Then the polynomial, then this field generated by f and a is nothing but fx mod the polynomial, mod this minimal polynomial, and every element in this field can be uniquely expressed as a degree d minus 1 polynomial expression in A. We'll continue. We'll see next time that this sort of has an inverse.